All right, everybody, hello and welcome to our next topic, which is confidence intervals. So we talk about confidence intervals now because they use both the Z and T statistic that we've been spending so much time on, and it's just another quick practical application of the Z and T statistics using the Z and T distributions and tables where we have expected values that we can draw from. So let's go ahead and talk about what they are first. So confidence intervals, very kind of roughly speaking, is a range of scores, an interval being a range of scores that is likely to include the true population mean. So confidence intervals are based around sample means, and they give us a range of scores that we would expect our true population mean to lie within. Of course, within some margin for error. Of course, we've done plenty of talking about margin for error in this class so far. So more precisely, it's a range of possible population means from which it's not highly unlikely that you could have obtained your sample mean. That's a bit of a mouthful, isn't it? But it's basically saying, right, if we don't know what the population is, right, the population's some enigma that we're trying to address, a confidence interval uses probability and R sample means, and things like variability and error, in order to create a range that we would expect if our sample is at all representative of our population. So, confidence intervals come with confidence limits. We're going to calculate an upper and a lower value of our intervals, right? A lower value that we would expect our scores to be like, or an upper value. So standard deviation and sample size dictate our confidence limits. So we'll go ahead and take a look at a formula here in a moment to kind of sort out how we find this. So I like this comic here because it's a little silly. But we are going to create confidence intervals for the 95% confidence rate and for the 99% confidence rate. However, if you want to be extremely confident in anything, you need to be relatively vague. So this is true of a lot of things, of knowledge. But definitely true here, that if we want to be 100% confident that something is true, that's pretty difficult to do, right? Because we know that probability can rear its ugly head and kind of prove us wrong in some ways. So here we have a curve, right, a normal curve. This is a Z distribution. So the Z distribution, if you remember, is kind of broken down already in such a way that we know what percentage of data falls under which parts of a distribution. So if we're looking for something like a 95% confidence interval, we're basically looking for the bounds, right, upper and lower limits, in which 95% of the data are contained. So this might sound a little bit complicated, but the process here is not unlike what we've already done when looking for, say, cutoff values. We're looking for cutoff values or portions of the curve that case or surround whatever percentage of data we're looking to surround to create our confidence interval. So again, this is all just conceptual, and we're going to actually practice this and calculate them in a moment here. So we have a couple of formulas. We can do this with Z and with T, and we will go ahead and do it with both. So for the Z distribution, if we want to have a 95% confidence interval, we need to use a Z-score where 5% of the area under the curve is in the tails. That should be tails with an S. I'll go ahead and fix that, but tails with an S. So that sounds familiar, doesn't it? That's like conducting a two-tailed hypothesis test. All right, so if we have a 95% confidence interval, we want 5% of the area under the curve in the tails. All right, likewise for 99%, we would want 1% of the area under the curve in the tails. And for the T distribution, if we want 95% to be in the body of the curve, we need to use a T-score that reflects our degrees of freedom and is testing at an alpha level that's appropriate for our confidence interval. So as promised in this class, we'll only be using alpha values of 0.05 and 0.01. So we'll be doing 95% confidence intervals with alphas of 0.05 and 99% confidence intervals with alphas of 0.01. Again, we'll demonstrate this in just a moment here. So for both of these tests, we're using two tails, or looking in the, say, two-tailed column, because as I'll indicate on a normal curve, we're looking for an upper and lower bound. So if you take the z distribution, for example, we're going to look for a bound that's on the positive end of the curve and a bound that's on the negative end of the curve. So we're looking in two tails. So let's go ahead and give this a shot. We have these two formulas here. They're both the same except for whatever statistic we're using. So we're taking the mean of a sample. We're going to add and subtract, all right? Add and subtract a term that we're going to calculate here. So we're going to calculate S, or standard deviation, over the square root of n. That's something we've seen before, and that's actually something called standard error. We have mentioned this at some point in the past, but we're going to calculate standard error, and we're going to multiply it by a statistic, either a z or a t value, that indicates the probability that we're looking for, right? Whether it's 95% confidence or 99% confidence. So these formulas act very similarly, so let's go ahead and talk about them. Let me hop over to the whiteboard here, and let's consider a few things here. All right, so let's start off with t, why don't we? We were working with t most recently, so let's start off with t. All right, so we're going to get a confidence interval. I'll call them CI. All right, so we're going to get a confidence interval. If we're going to do that, we need some sample mean, plus and minus, a t statistic that indicates the correct percentage. Then we also need to multiply that t by the standard deviation over the square root of n. All right, so remember what we're really doing here is trying to find a range of values that we are whatever percent confident, right? 95 or 99% confident, contain the true population mean, all right? And we do that by using not just the mean itself, but by using the standard deviation and the sample size. Remember, sample size is important here because the larger our sample size, likely the closer we are to understanding what's really going on in the population. So let's go ahead and start by calculating a 95% confidence interval. All right, and this is somewhat like it sounds, right? We're going to come up with a range of values. And at the end of the day, what we can say is that we are 95% confident that the true population mean lies within these boundaries. So let's go ahead and give this a try. So let me give some values here. Let's say we have a sample of 15, a mean of 149.3, all right, and a standard deviation of 4.7. Okay, so let's say that these scores are from, let's call it the GRE. I think we talked about the GRE a little bit recently. The GRE is the Graduate Record Exam, which is a exam that you need to take, a standardized exam that you need to take in order to enter most graduate schools. So let's say that these are our GRE scores, okay? So these are GRE scores. Let's say that you're looking at a specific sample. Let's say that you're interested in, say, a minority sample or a group that's maybe taking the exam less than others. Let's say that we're looking at international students, right? The GRE is a US-based exam, so you want to take a sample of 15 international students and see how they're doing. And then you want to kind of extrapolate this or make a greater assumption about how the entire population of international students might perform on this exam. So let's take a look at the values we have here. We have n, all right, we have x bar, and we have s. So if we go look at the formula, we have x bar, we have s, and we have n. So the only thing that we're missing is t, okay? So we're missing t. So how do we get t in this case? Well, we get t like we're looking for, say, a cutoff score. So how did we get a cutoff score for t? Let's think about it. So if we wanted a cutoff score, we needed a few things. We need the alpha level. So if we're testing at a confidence interval of 95%, we already know what type of alpha level we're working with. We're working with an alpha level of 0.05. And how do we know that? Because an alpha level is a percentage, all right? So if we want to be 95% confident, there's going to be 5% of the data off in the tails that we're not going to consider. All right, we're basically finding the boundaries for a null hypothesis here. All right, so to find a cutoff score, we need an alpha level, right? We have that. We need the number of tails. Remember, confidence intervals are always going to be two-tailed. Let's go ahead and draw out why that is. All right, so if this is your null hypothesis and your population mean is supposedly here, you would have a bound here and a bound here. So remember, if we find anything, if we do a hypothesis test and we find anything in here, that's evidence to suggest that the null hypothesis is true. So those are really the values that we're looking for. All right, we're looking for the values that fall in between here. This will be our confidence interval. In fact, 95% of the data will be right in here. So we're creating boundaries on the curve, scores that we would expect to get 95% of the time if the null were true. All right, so that's why we have two tails, all right, because we're looking above and below the center of the distribution. And then the last thing we need is degrees of freedom. So we have to kind of dig back in our head here about how do we get degrees of freedom for t. Well, degrees of freedom relies on your n. So degrees of freedom is generally just n minus 1. That's what we need to do here. All right, degrees of freedom equal to n minus 1. Remember, if you have more than one group, you would subtract more than 1. But that's not what we're dealing with here. So we've got something like 15 minus 1 gives us 14. Okay, so we have 14 degrees of freedom. We have two tails. All right, I'll write it over here. Two tails. All right, two tails, and we have an alpha of 0.05. So we can actually head over to the t-table, and let's go ahead and do that. Our old friend, the t-table. All right, so remember, there are two different columns here that we can consider, the one-tailed and the two-tailed. We already established that we need to be in the two-tailed column. We're at an alpha of 0.05 because we're looking for a 95% confidence interval, so only 5% out in the tails. And we have 14 degrees of freedom. So I'm going to go ahead and just scroll down to where we have, all right, so we're looking on the right-hand side under the two-tailed test, two-tailed test on the right, looking in the middle of those three columns, the 0.05, and we're going down to where there's 14 degrees of freedom. And if we do that, we find a value that looks like 2.145. 2.145. So let's hop back over to the whiteboard. So if we go to the t-table, the t that we need is equal to 2.145. This particular score, all right, so remember we're going to use plus or minus on this t. So this particular score is going to mark, okay, this boundary that we're interested in finding and this boundary that we're interested in finding. But we don't just want to keep this in the t metric. We want to actually create a range of scores around this mean. Okay, so this is where our formula comes into play. All right, so let's actually start plugging into this formula. So our confidence interval is equal to, let me go ahead and write it out. So 149.3 plus and minus this term that follows. So that'll be that t to indicate the percentage of the area under the curve we're looking at. And then we need to get what we call the standard error, the standard deviation over, right, so the standard deviation is 4.7 all over the square root of 15. So let me go ahead and continue to solve this, and I'll actually show you what I would normally do in this case. Because this is sort of treated as a separate term, I like to calculate this separately, and this is called standard error. So I might just do my own little standard error calculation over here before I even put it into the formula. This is what I like to do. You don't have to do this. But then we get something like 4.7 over 3.9, and we get a standard error equal to 1.2. Then we're multiplying by 1.2 here. All right, so remember our order of operations. The first thing we want to do is get rid of our parentheses. So if we continue to solve here, we still have our 149.3 plus or minus, and we would multiply these together, and we would get something like 2.574. All right? So what we're going to do when we do this is we're going to add this term, 2.574. We're going to add it to our mean, and we're going to subtract it from our mean. And then we're going to report these in a certain way as well. So let's go ahead and set both of these up. Let's go ahead and subtract and add these values here. All right, and what do we get? So for our lower bound, we get something like 146.87. And remember, if you're rounding, it's a little different than mine. Don't worry about it. Just make sure you're rounding consistently, and we'll make sure that you're good to go here. So 146. Oh wait, not 87. Look at me go, talking about the incorrect decimal here. 0.73. 73 we got here, but no less. Right, if you're a little bit off, all right, I think we all know what like too far off is, right? But make sure that you're close to this, right? But if you're not exactly, no need to panic. We'll do the same thing here, 151.87. Okay, so these are the lower bound and the upper bound of this confidence interval. So we would report this like this. We would do some parentheses. We would say, okay, the lower bound is 146.73. The upper bound is 151.87, right? And then what does this mean? We are 95% sure that our population mean is within these boundaries, our population mean for this sample. So remember, 95% sure is not 100% sure, but it's pretty good, right? It's pretty good to say that you're 95% sure of something, 95% confident. And somewhere where we see these confidence intervals a lot is in polling practice, right? They'll maybe give a value or an average or a polling number and say we're 95% confident that this is evident of the entire population. But we know how well polling accuracy goes, so take it with a grain of salt. But this is the process, right? Finding boundaries around a mean, using a t-value, using variability like standard deviation, and using sample size to determine what values we might expect. So let's go ahead and try one more thing with this data here. Let's go ahead and just try and get a 99% confidence interval for this data as well. So a 99% confidence interval, okay? So we'd be using an alpha of 0.01, right? Because 1% of the data will be in the tails and we're looking for the rest of that data. So remember, if we have a curve here, right, we're looking for where 99% of the data is here. And we're looking for the values that would mark these boundaries. So first we need a t-value that would mark those boundaries. And in fact, if we look back at the formula, all right, if we're using the same data, the same n, the same mean, and the same standard deviation, we're using all of these things. The only thing that's going to be different in this calculation is that t-value. So let's go ahead and get that t-value so we can get on with it here. So you need degrees of freedom again, all right? So degrees of freedom is equal to n minus 1. We're still at 15, so we're at 14. It's still two tails, right? Because confidence intervals will always be considered a two-tailed analysis. And then we need the alpha value, which is given here. So let's hop over to the table. So we're still over in the two-tailed test side, all right? The two-tailed test here. So now we're over in the far right column, the 0.01. All right, 0.01, and we're still scrolling down to 14 degrees of freedom. So we see something like 2.977. 2.977. Let's go ahead and pop that over on our whiteboard. So that t that we're looking at is equal to 2.977. All right, so everything's the same except for the t. So let's go ahead and work this out. So the confidence interval is equal to our mean plus or minus that t-value we just grabbed. And this value is even going to be the same here because our standard error, all right, what we got here has not changed, right? It's the same standard deviation, it's the same n. So that's the same. So this is what we would need to do. We would take 149.3 plus and minus. If we multiply these together, we get 3.572. So we would go ahead and subtract 3.572 and add 3.572 to our values here. So let's go ahead and do that. So our lower bound will look something like this. Our upper bound something like this. All right, let's go ahead and write them in the format where we normally would see these in. Something like this. So let's take a look here. 145.72, 152.87. If we look back here, this is a narrower range, right? The 95% confidence interval is narrower. And that makes some sense, right? Because if you want to be more confident and you widen your range, the more likely you are to be correct, all right? So let's think about one more kind of interesting confidence interval idea. What if we wanted to be, say, 100% confidence? What if we wanted an 100% confidence window? Well, because statistic relies on error, statistics are always filled with error, the only way that we could ever be 100% confident that a true value is between two values would be something like this, right? Negative infinity, positive infinity, of course. Negatives and positives on infinity don't make much of a difference, but this is the general idea that we can possibly be 99.99999% sure, but we have to really widen our range to many possibilities. So there's lots of different data that we can calculate confidence intervals for, but no matter what, according to the laws of mathematics, if we want to be 100% confident about anything, we need all possible values in there. So let's go ahead and try out confidence intervals with the z-statistic as well. All right, so our formula for a confidence interval using z is exactly the same, except for instead of using t, we are using z. And z is a little bit easier because remember z comes with some sort of predetermined cutoff values because z is a standardized metric. So let's go ahead and get a curve going here and I'll remind us of what we're working with here. So if we wanted to get a 95% confidence interval, I'm going to do dotted lines for this. All right, 95% confidence, remember it's always going to be two tails. All right, so 95% confidence here. In fact, for continuity's sake, let's keep this dotted. All right, dotted line. All right, so in here we have 95% confidence. All right, so if we remember all the way back to our z-tests, if we were testing a z-test at an alpha of 0.05 and it was a two-tailed test, there was a certain value we would use. All right, it's the same here because z is standardized. All right, if we want 95% of data within these bounds and 5% of the data in the tails, these are the z-scores that mark those boundaries. And likewise, if we wanted to have a more conservative cutoff value, right, something more like this, where we have 99% of scores, this would be an alpha of 0.01, only 1% of data out there in the tails, and we would have scores, all right, these are a little stacked on each other, but negative 2.58 and positive 2.58. All right. So these are our boundaries that we will be using. So let me go ahead and just write these down a little more clearly. If we want a 95% confidence interval, the z we want to use is plus minus 1.96. This is because this is a two-tailed test at an alpha of 0.05, right? And for 99%, same story, except at an alpha of 0.01%. So we would have our plus minus 2.58. So these are the only two z values you would use to calculate confidence intervals. So let's go ahead and get another set of data. Let's stick with our GRE example, some more GRE scores. Let's say that you sampled from a group of, let's say, young people taking the GRE, all right? The GRE you usually take after you complete your undergrad degree, so let's say we're talking people in their early 20s, so younger than 25, let's say. And let's get some data going here. Let's say the average scores here are 127.3 with a standard deviation of 19. And get this, we're going to have a big N here. Let's say that this time you're not messing around and you want a big N. So remember, sample size contributes to significant findings. The more data we have, the more likely we are to find something significant. the more data we have, the more likely we are to be closer to the true population. So bigger sample size kind of means a lot. All right, so let's go ahead and now that we have this, so thinking of our formula, we have this, we know what z we're going to use. So let's go ahead and get standard error. Let's go ahead and get this piece here. So if we get this piece here, all right, s over the square root of n gives us 19 over the square root of that big value. So we get 19 over 59.45, giving us 0.319. So remember, this is going to be the same regardless of which confidence interval we decide to calculate. So let's go ahead and calculate a 95% confidence interval. Let's get a 95% confidence interval. So remember, this is relying on an alpha of 0.05, right? 0.05. So our confidence interval would be equal to 127.3 plus or minus that 1.96. Remember, that's what we're using for this here. 1.96 times that standard error of 319. All right, so 127.3 plus and minus, what do we get? Something like 0.625. All right, so if we take 127.3, I'm getting a little squished here, but that's okay. Let's take 127.3 minus 0.625, and then 127.3 plus 0.625. All right, little squooshed, but it's okay. Let's go ahead and get those boundaries. So for our lower boundary, we would get something like 126.67. For our upper boundary, 127.92. All right, so let's go ahead and write this out. All right, so notice how small this interval is. Why is it so small? Well, it's so small because we have so much data, right? If we have this much data and the mean is this, the likelihood that the population mean is significantly different than this is pretty unlikely. It's possible, and in fact, it's 5% unlikely, right? Because we are 95% confident. And of course, this isn't just based on the mean value, this is based on the standard deviation and the sample size. So there you have it. And let's go ahead and try just once more, but let's get a 99% confidence interval. All right, so this corresponds to an alpha of 0.01. So we'll calculate in the same way, except we're using our other cutoff value. And remember, if we went to the z-table, we could find this. If we went to the z-table and we looked up where this is an alpha of 0.01, if we looked up where there's only a 0.5% over here and a 0.5% over here, it would lead you to this value, right? So if you're feeling confused about where this value comes from, go find it in the z-table and you'll see and hopefully remember when we talked about this before. But that's how we're getting that here. So we'll take here our mean. We're going to get that z value in here. And then we're going to multiply by that standard error. So we get something that looks like this. All right, we're going to take 127.3 and we're going to subtract 0.823. We're going to take 127.3 and we're going to add 0.823. We're going to get our lower and upper bound. So we get 126.48 and we get 128.12. So let's go ahead and put that in our nice little format. We got 126.48, 128.12. So notice that this is a wider range, and remember that is because we are more confident. If you want to be more confident, you need to widen up your range. That's what we were talking about back here with infinity to infinity, right? If you want to be completely confident, you need a wide range. But notice this range isn't huge. It's still pretty concise, right? Which is somewhat amazing. Considering how much data could be out there for any given data set, right, or any given population. So remember that these boundaries specifically indicate what we would expect our population mean to be given the data that we have. All right, so that concludes confidence intervals, just a little bit of information about how we can continue to use the T and Z statistics outside of hypothesis testing. All right, as always, let me know if you have any questions on this material.